let's go ahead and talk about Ohm's Law here. So Ohm's Law states that the resistance of a metallic conductor is constant, and the current flowing through the conductor is proportional to the voltage or potential difference across it if the temperature is constant. This is the key point to Ohm's Law, and the IB physics exam loves to test this concept. Right? The resistance does not change if the temperature is constant in metallic devices. Alright, the equation for Ohm's Law is either sometimes written as R equals V over I, or V equals I times R. And so Ohm's Law states that the voltage is proportional to the current. So if I increase the voltage, the current goes up, resistance is constant. They always test this concept in one way or another on the IB exam. So once again, current changes if voltage changes. The resistance does not change. Alright, once again, if a device follows Ohm's Law, if I change the voltage, I change the current. The resistance does not change. If I increase I, then I also increase V, and vice versa. Resistance does not change. And this is only true when temperature does not change. Many physics students have this idea, oh, Ohm's Law, V equals I times R, but they forget the most important part of Ohm's Law is that it only holds true at constant temperatures, and R remains a constant. So let's talk about ohmic and non-ohmic devices. So ohmic devices are devices that obey Ohm's Law. Non-ohmic devices are devices that don't obey Ohm's Law. So example of non-ohmic devices would be filament lamps, diodes, and thermistors. Now, on an IB exam, most likely what they're going to do is give you a graph and say which one obeys Ohm's Law, which one doesn't, or vice versa. And so, graph A here, this is going to be linear, right? And it makes sense that it goes, it goes through the origin. Makes sense it goes through the origin because at zero current and zero voltage, there should be no resistance ideally. Alright, so if it's linear, if you're graphing I over V or V over I, doesn't matter. Because it's a linear relationship, you should get a straight line through the origin. Graph B is a lamp filament, nonlinear. Graph C here, on the bottom left, that is a diode, nonlinear. And graph D, that is a thermistor. And it makes sense to basically maybe memorize some of these patterns because they may ask you which one of these is a lamp filament. And you go, well, lamp filament makes that little curvy graph that B makes. Or a diode is very weird looking. Once again, the key idea here is that for Ohm material, I versus V is a straight line because R is a constant with that straight line with that the slope of that line, which would be V over I, will be equal to R. And R is a constant, and so the slope is constant, which is what we call a linear relationship. Alright, so Ohm's Law in wires, right? So experiments show that three factors affect the resistance of a wire calculated at a constant temperature. They are the nature of the material, which is the specificity of the material, which we call rho here, the length of the wire, and the cross-sectional area of the wire. The cross-sectional area of the wire is, once again, is pi r squared. So resistance in Ohm's Law, R equals rho times the length divided by the area. Now, it makes sense that an increase in area would decrease the resistance. Hence, this little diagram right here that I included. For thin wire, you have like one lane of traffic. Thick wire, you have more lanes of traffic, more space to move around. Alright, and so you decrease the resistance, less room to bump into each other. However, why do you think increasing the length would increase the resistance of the wire? And as we talked about in class, we said, well, when you increase the length, there's more opportunities to bump into electrons. You're going to hit the walls more as you travel a further distance. So you tend to slow down a bit. That's why increasing the length would increase the resistance of the wire. Alright, electrical power. Recall from topic 2.3 that power is the rate at which work is done. Electrical power is the rate at which electrical energy is transferred by an electric current. Electrical power is measured in watts. Alright, and recall from topic 2.3, the unit of watts is joule per second. And remember, the work done on a charge is Q times V. Well, wait a minute. If work is Q times V, and P equals Q V over T, work divided by time, well, is it Q divided by T I? Wait a minute. That means I know that power, that is current times voltage. Alright, power is current times voltage. It's good to memorize certain things, like work is Q times V, and power is work divided by time, and we know that QT is going to be I times I, so you get I times V, so power is I times V. However, electrical power can also be written in terms of resistance. So for example, we have P equals I times V. We know that V equals I times R. So then our equation becomes, well, plug in IR for V, we get P equals I times R, which is I squared R. I want you to figure out how you can write power in terms of voltage and resistance. I want you to think about that one. Once again, substituting what you can plug in for I. Alrighty, and that is just a quick overview of Ohm's Law.